Hey Jugal,
Yo,
yo, I'm thirsty.
I got you.
Hello there, my name is Raymart Datuin.
I'm Jake.
I'm Aizaz.
And I'm Jugal.
And we are
Cypher Team.
and this is
Cypher.
Have you ever ridden a bike? Have you ever balanced a broomstick on your palm?
Or have you ever just stood up?
These are all real-life examples of an inverted pendulum. Inverted pendulum is a system that constantly works against gravity to stay balanced. It seems effortless to balance, right? But have you ever stopped to think about how the balance is maintained? The inverted pendulum is one of the most fundamental problems in control theory. It happens all around us. But we often overlook it because our brains make balance feel second nature. Our bodies solve this fundamental problem by constantly using feedback and motion. Cyper was designed as a low-cost, real-time robotics platform for learning control systems. Our main goal? Create a modular, battery-powered robot that can balance on its own using only a few sensors and smart software. At its core is a Raspberry Pi 02W running our PID controller, tuned using real-time sensor feedback from a filtered 9-axis IMU using Magic filter. Motor control is handled by dual brushless DC motors and a DRV 8871 motor drivers. Power is isolated between the CPU and the motors using separate power systems. Now, what the heck is a Magic filter? And also, what the heck is a PID?
PID consists of proportional integral derivative. It is a control algorithm that continuously adjusts the system output to minimize error. Proportional. It reacts to how far the system is from the desired station or goal. The bigger the error, the stronger the correction. Think of it as an immediate push towards the balance. Integral. It reacts to how long the error has been present. It adds up past errors to eliminate steady-state drift. It remembers and fixes bias over time. Derivative. It reacts to how fast the error is changing. It slows down the correction to prevent the overshoot. It acts like anticipation, like it dampens sudden movements. What is a low-pass filter? A low-pass filter is an angle processing tool that removes high-frequency noise and lets low-frequency signals pass through. IMUs can pick up small, fast vibrations that cause filter to pick up noise in the data. We use low-pass filter to help smooth out the data that's being used in our data processing.
IMU collects very noisy raw data that jumps around. Gyroscopes drift over time, accelerometers respond to movement and gravity, and can't tell the difference between the two. Magnetometers are affected by nearby metal and electronics. The Magic filter blends all these inputs to cancel out their weaknesses and produce a clean, stable orientation estimate.
So how does our robot balance itself? Well, it uses an onboard IMU to determine the current angle of the robot. It uses a gyroscope and an accelerometer blended together to give us the current angle of the robot, whereas this would be 0 degrees and this would be about 15 degrees. Now, the PID uses a proportional integral derivative terms. So the proportional term corrects for current errors in the system. The integral term corrects for past errors, and the derivative term corrects for future errors. Together, they come up with an output which sends a motor output to both of the motors, which will correct the error in the angle. So an angle of this much will get a proportional integral and derivative term that's sent to the motors to correct it. The algorithm runs at about 100 hertz, so 100 times per second to keep the robot upright. Now I'll demo how this would work. I'm going to put the robot down. I'll run the algorithm. It'll take a second to adjust, and then I can let go. And look at that. The robot's able to balance itself. So on top of creating a self-balancing robot, we implemented a web dashboard to help visualize the current angle of the robot and to be able to just adjust PID values on the fly. It also has the ability to control the direction of the robot to make it move backwards and forwards with the joystick. If you come on here, we'll show the web dashboard. It's showing the current angle of the robot and that red dotted line being 0 degrees. We see that it oscillates back and forth to keep itself balanced. If we go down, we also have the ability to see each one of the P, I, and D terms, and this can allow us to debug and see what needs tuning. We can update these parameters in real time right here. We can modify these values and update them, and they'll be seen in real time. Now, on top of this, the joystick we can use on our phone. So, if we look at my phone right now, we here have the joystick and the robot. I can push the joystick forward, and the robot will slowly move forward. I can move it backwards as well. And this allows us to control the robot.
After some time tuning the PID, Cypher successfully balances from startup within 5 seconds and recovers from angles of 15 degrees. It can continuously run for 12 minutes on a full charge and adjust itself dynamically. While minor oscillations remain during aggressive pushes, the system is robust and responsive, just as we planned.
Our first proposed enhancement is to add a second inverted pendulum, doubling the control complexity and enabling exploration of advanced strategies like linear quadratic regulator.
Next, we plan to integrate computer vision, allowing Cypher to recognize objects or even follow people in real time. And we are going to do that by either integrating a remote camera or an onboard camera.
So we're also developing a Bluetooth app that allows users to control the robot, monitor sensor data, and tune PID values all from their phones.
Ultimately, Cypher is a flexible embedded platform that supports exploration and validation of advanced control strategies in real-world robotic systems.
We're proud of what Cypher has become, a real-time embedded control system that went from a concept to a working prototype. Throughout this journey, we learned the value of iteration, collaboration, and hands-on engineering. Thank you to our advisors, instructors, and supporters who guided us through the process. And thank you for watching.
Hey everyone, this is Dr. Steven Knudsen. He is our client, and he has a PhD in digital processing. He is blessing our project.
So this fine robot, may she be error-free and her filters be stable and reliable. Bless you, robot.
Advanced strategies like linear quadratic visual abilities.
Why did it die?
It's just
Thirsty. I got you.
One sec. You guys, I didn't do anything.